Now that we have known about solutions in different forms, we would like to stick to one of the forms just to be consistent. Although, since all the forms are equivalent, you can choose any form you like to work with, and you'd still get the same results all the time. So, particularly, would like to stick to this form A sine omega naught t plus delta. In this video, I'll be discussing the physical characteristic of this system, and one of the things that I'd like to explore, I think most of you should know this fact if you want to know minimum amount of physics about simple harmonic motion, is the fact that a one-dimensional simple harmonic motion, simple harmonic oscillator, rather accurate to say, one-dimensional simple harmonic oscillator is a conservative system. What I mean is this system conserves energy, or the energy is conserved throughout the motion of the system. And we know that energy of a mechanical system is the sum of the kinetic energy, which is written by T. So T denotes kinetic energy, plus V, where V denotes potential energy. And E denotes the total energy. And we'd like to find the total amount of energy that's stored in a simple harmonic oscillator. And in general, energy can be a function of time, but if it is conserved in time, it will be a constant with respect to time. That means with time, it doesn't change. So if E is constant, we do have a conservative system, alright? So that's what we are supposed to do. And in the case of simple harmonic motion, it's incredibly simple to show that a simple harmonic oscillator is indeed a conservative system. So how? We know that T is equal to half mv squared, and those of you who are familiar with the dot notation, this is V is simply the first time derivative of the position, and therefore this is also written as half mx dot squared. And since x is given by the expression we have here, x dot is simply omega naught a times cosine of omega naught t plus delta, and if you square it, you simply get omega naught squared a squared cosine squared omega naught t plus delta. So multiply half m with it, and that gives us the kinetic energy, and we get m divided by 2. However, remember, omega naught squared is equal to k divided by m, and so this quantity here simplifies to, so the kinetic energy becomes half k a squared cosine squared omega naught t plus delta. What about the potential energy? The potential energy is basically the amount of work that is required to extend the spring from position 0 to x. So the amount of work required to pull the mass attached to the spring from 0 to x. That's our potential energy. And we all know that the explicit expression for potential energy, specifically the differential potential energy, is equal to negative F times dx. And of course, from the Hooke's law, we know that F is simply the restoring force, which is negative kx, and that gives us positive kx times dx. So if we do integrate it from 0 to x, we get k integrated over x from 0 to x, and x dx. Of course, x is the variable of integration, and in order to differentiate the variable of integration from the limit, we put a prime on x, and that will give us half kx squared when we put on the limit. So if I plug in the explicit expression for x into this equation, that gives us v equal to half k a squared sine squared omega naught t plus delta. So notice, if we now plug these expressions into the expression for total energy, what do we get? We get half k a squared cosine squared omega naught t plus delta. So this is the expression for kinetic energy, but also this factor is common both in kinetic and potential energy, so we simply factor it out and write cosine squared omega naught t plus delta, and then sine squared omega naught t plus delta. And of course, the quantity in the square bracket gives us 1. So finally, we have the total energy of a one-dimensional simple harmonic oscillator to be this. And this is, of course, a constant. And therefore, the one-dimensional simple harmonic oscillator is a conservative system. Not only E is independent of time, emphasizing on the conservation of energy, but it is also proportional to the square of the amplitude, which is a great result, by the way. And there are only few systems in physics which can be solved explicitly, and one-dimensional simple harmonic motion is one of them. Speaking of the physics of the system, notice that in oscillation, a sine omega naught t plus delta, this remains the same if we add a phase angle of twice pi, right? Also, if after time tau, the system returns to the position when it was at time t, then tau is called the period. And because these two things are equivalent, then the period times omega naught should be equal to twice pi, which gives us an expression for the period in time. So the period is given by twice pi divided by omega naught, which is the same as twice pi square root of m divided by k. The frequency of the simple harmonic motion is defined to be the inverse of the period. So the frequency nu naught is equal to 1 over tau. So this is 1 over twice pi square root of k divided by m. And of course, this is related to the angular frequency by this relation, omega naught divided by twice pi. Notice that the period here is independent of A. Equivalently, it can be said that the period is independent of the energy. When this happens, the system is called to be isochronous. So isochronous means the system is independent, the period is independent of the amplitude, or equivalently the energy. In the next video, I'll be talking about an application of the simple harmonic motion, and that is in the context of pendulum. And also, there are confusions relevant to the terminologies, especially as we'll see, the angular frequency and angular velocity are two different things, but often people confuse them by thinking that they are the same quantity, but of course angular frequency and angular velocity are completely different, and in the next video we'll be clarifying that for you once and for all. So until then, take care. If you think that the contents on this video has helped you, please give it a like and subscribe to this channel. We'll be coming back to you with more videos. Until then, goodbye.